So there's a question. The following particulars relate to a two-cylinder locomotive, right? Now we have two-cylinder locomotive with two coupled wheels on each side, right? Now it has only two coupled wheels. So either it can be a driving and trailing wheel, right? So two coupled wheels on each side. So these are data given. Stroke length 650 millimeter. Mass of the reciprocating parts per cylinder 240 kilogram, right? So we need to consider these terms very carefully. It's mass of reciprocating parts per cylinder, and it's two-cylinder locomotive, right? So here the reciprocating parts is 240 kilogram, and mass of revolving parts it's 200 kilogram. Mass of each coupling rod that's 250 kilogram, right? Each coupling rod. So now we have two coupling rod on both sides, right? That is 250 kilogram each one. The radius of center of coupling rod pin, right? So I told you it can be considered as rotating mass. Why? Because the pin of the coupling rod would be rotating in a circular path, right? So this can have a radius, right? So that's why it's given radius of center of coupling rod pin. It is 250 millimeter. The distance between the cylinders 0.6 meter. Okay, so now we have two cylinders, that is 0.6 meter. Distance between the wheels, that is 1.5 meter. So from this we know that this is inside cylinder because the wheels are outside. This is 1.5 meter and this is 0.6 meter. And the distance between the coupling rods it's 1.8 meter. So coupling rods would be somewhere here further outside, right? That is 1.8 meter, right? So this is how the schematic of this the data is going to be, right? Now we'll see what is the question. The main cranks are at right angles and the coupling rod pins are at 180 to their respective main cranks. So main cranks are at right angle, right? And the coupling rod pins are 180 degree to their respective main cranks. If I consider this as main crank 1 and this as main crank 2, right? The coupling rod of main crank 1 is 180 degree to the respective main crank, right? And for this one M2, this would be 180 degree for that respective pin, right? So this is how these masses are going to be located, right? The balance masses are to be placed in the wheels at a mean radius of 675 millimeter, right? So now the balancing masses are going to be placed at 675 millimeter, okay? In order to balance the whole of the revolving, right? Now we have the revolving mass that is 200 kilogram, right? So the whole of the revolving and 3/4 of the reciprocating masses. So in the reciprocating mass only 3/4 is going to be balanced, and revolving part it's completely going to be balanced, right? The balance mass for the reciprocating masses is to be divided equally between the driving wheels and the coupled wheels, right? So in the question it's given we have two wheels, right? One is driving wheel and the other one is trail wheel. Both are coupled. So now the balance masses are expected to be distributed equally to this and this, right? Is to be divided equally between the driving wheels and the coupled wheels. First question, find the magnitude and angular positions of the mass required for the driving and trailing wheels, right? So as usual, we have to find the balancing mass which is required for both driving and coupled wheels. And the hammer blow at 120 kilometer per hour. Right? So now the speed is given 120 kilometer per hour, and we have to find the hammer blow. If the wheels are 1.8 meter diameter, right? So the wheel diameter is also given. Right? So now we'll see how to solve this, right? I'll give you like 1 minute. You just take this data, the stroke, the mass of reciprocating bars, mass of revolving bars. That would be easy. Right, so if you have noted this data, we'll see how to solve it. Right. So given LC is equal to LD is equal to 650 millimeter. So that is stroke length is equal to 650 millimeter. Right. So since we have two cylinders, so each of it is 650 millimeter. They are considered as C and D. Right. So they are the cylinders. And since the stroke length is 650, we know the crank radius is half of that. That is 325 millimeter. Right. 325 millimeter. And mass 1 it's given 240 kilogram. That is mass of reciprocating parts 240 kilogram, and mass in revolving parts it's 200 kilogram. Right. So M1 is 240 kilogram and M2 is 200 kilogram. M3 that is the mass of the coupling rod, that is 250 kilogram. Okay. And radius is given 250 millimeter. Radius of the center of the coupling rod pin, it is 250 millimeter. Right. So that radius we will consider as A and F. Right. So they are 250 millimeters. CD is equal to 0.6 meter. Right. The distance between cylinders is 0.6 meter. Distance between wheel is 1.5 meter, and distance between coupling rod is 1.8 meter. So we'll put this data also. Right. So distance between cylinders is 0.6 meter. CD. Distance between the wheels is 1.5 meter. That is BE. And the distance between the coupling rod it is AF 1.8 meter. Right. And the balancing masses are expected to be placed at 675 millimeter radius, and also C is 3.4. That is only 3 by 4 of the reciprocating masses are expected to be balanced. Right. It's given the question, right? Yeah. The whole of the revolving mass and 3/4 of the reciprocating masses are to be balanced. So C is equal to 3 by 4. Right. So these are the data given. Okay. So now we'll see how to draw the polygon and solve this numerical. So as usual, we'll first decide which uh, draw first, whether the polygon, couple polygon or force polygon. Before that, we have to draw the planes as well as the position of the crank, right? So we'll first do that. So we have the position of planes here, right? So we know the distance between the cylinders are 0.6 meter, that is CD equal to 0.6 meter. Then the distance between the wheels are 1.5 meter, right? So the wheels, wheel 1, wheel 2, that is BE, that is equal to 1.5 meter. Then the distance between the coupling rods are 1.8 meter, right? So AF is 1.8 meter, right? So you may wonder why these names are selected in such a way, CD, BE, AF, right? That's because here, if you see, if you can draw like this, we will be having in a nice order, right? A, B, C, D, E, F, like that, right? So that's why it's taken like that, right? CD, the cylinder length, distance between the cylinder, BE, the distance between the wheels, and AF, the distance between the coupling rods, right? So based on these data, you can divide these distances accordingly, right? So BC is 0.45 meter and AB is 0.15 meter, right? So this is position of planes. Now we have to position the cranks, right? So angular positions of cranks and coupling pins. Okay. So in the numerical, it said the cylinders are at right angle. So CD is at right angle to each other, and the coupling rods are 180 degree from its respective cylinder, right? So if I consider C, the coupling rod is A for that one, and if I consider D cylinder, the coupling rod is F, right? 180 degree. Okay. So this is the known masses. Now we have to balance with two unknown masses. So that's X. So we can have X and Y or something. Since it is symmetrical, right? Since it's symmetrical, if you draw an axis here, you can see it is symmetrical. It is considered as X and X. You can have another name, X and Y, right? Doesn't matter. Okay. Right. From now we can we have the planes as well as we have the positions. So we can go for the table. Right? So for that, we need to consider any one of the plane as the reference plane. So for us, B and E are the unknown, right? So I'll consider any one of these B or E as the reference plane. So I'll consider B as a reference plane, right? So from B, this side is considered as negative and this side is considered as positive, right? So from B, the cylinder A, the coupling rod A is negative and rest of the masses here are positive, right? So we'll fill this data first in the table, right? Let MB and MB and ME be the balance masses, right? So MB and ME are the balance masses placed in the driving wheels B and E respectively, right? It is asked in the question to distribute the masses equally. Masses is to be divided equally between the driving wheels and the coupled wheels, right? So now we have to divide it equally. So first we'll go with the driving wheel, right? So here we have the planes, masses, radius, centrifugal force, distance from the plane, and the couple, right? So first we'll calculate how much of the mass is need to be balanced, right? So accordingly, we know that the mass of the reciprocating parts per cylinder is to be balanced is 3 by 4, right? So that is 3 by 4 into 240, right? So reciprocating mass it's 240. So only 3/4 of that is to be balanced. So that is 3 by 4 into 240, that is equal to 180 kilogram, right? So for reciprocating parts, only 180 kilogram is need to be balanced, right? Since the reciprocating masses are to be divided equally between the driving wheels and the trailing wheels, right? It's asked in the question, the reciprocating masses has to be divided equally between the driving and coupled wheels. What we have to do, we have to divide this one equally. So if you divide it by 2, you'll have 90 kilogram, right? Therefore, 90 kilogram is taken for driving wheels and 90 kilogram is taken for trailing wheels, right? So now we have to balance only 90 kilogram of the reciprocating mass for the driving wheel, and the rest of the 90 kilogram will need to be balanced in the trailing wheels. Now, for each driving wheel, the following masses are to be balanced, right? So we have to do the balance thing twice. One is for driving wheel and the other one is for trailing wheel, right? So for now, we'll calculate for driving wheels. For driving wheels, the following masses are to be balanced, right? Half the mass of coupled rod. Why half of the mass? Because other half is need to be balanced by the trailing wheel, right? So the mass of the coupled rod is 250 kilogram, right? And half of that is 125 kilogram, right? So the other 125 kilogram will be balanced by the trailing wheels. Why? Why? Because we know the coupling rod, if you have two wheels here, right, one like this and one like this, and a coupling rod which is joining these two, right? So the balancing would be need to be divided half, right? Half of that here and half of that here, right? So only half the balancing mass, half of the coupling rod will be balanced by the driving wheel. In other words, the masses at the coupling rods A and F to be balanced for each driving wheels are 125 kilogram, right? So for each driving wheel, only 125 kilogram is to be need to be balanced. Okay. So this is related to the coupling wheels, coupling rod, right? And all of the revolving masses, that is all 200 of the revolving masses need to be balanced, right? So the revolving masses is 200 kilogram and reciprocating masses we have calculated only 90 kilogram need to be balanced. So that means 200 plus 90, which is equal to 290 kilogram. So for each driving wheel, we have to balance 290 kilogram in sense of the whole of the revolving mass 200 kilogram plus reciprocating mass, that is 90 kilogram as per calculation, right? So we have to balance 290 kilogram. All right. So we can see here A, that is 125 kilogram. According to our diagram, A is the coupling rod as well as this one. F is also the coupling rod, right? So A coupling rod, F coupling rod, both of them are 125 kilogram. So we'll fix 125 kilogram in this table. A coupling rod 125 kilogram, F coupling rod 125 kilogram. Similarly, B and E are the balancing masses which we don't know. We have to find. So the masses are MB and ME. Okay. And the known masses which are need to be balanced in cylinders C and D, which is 290 kilogram. Right. According to what we have found, it is 290 kilogram. So for cylinder C as well as for cylinder D, the mass balances are 290 kilogram. Right. So now we have found the masses. Okay. The radiuses. Now the radiuses are also given. So we'll gather it from the equation. For the coupling rod, right? For the coupling rod, it's given. The radius of center pins of the rod pin is 250 millimeter. So that is equal to 0.25 meter, right? So that is here 0.25 meter. So for this coupling rod, it's 0.25 meter. For this coupling rod also, it's 0.25 meter. Right? And in the question, it is asked the balancing masses are to be placed at 675 millimeter. Right? You see here, the balanced masses are to be placed at the 675 millimeter. So the distance, sorry, the radius of the balancing masses are 675 millimeter. That's equal to 0.675 meter. So the reference plane, the mass there, B, that is 0.675 meter. And for mass E, the radius is 0.675 meter. Right. And the question it's given, since the stroke length is 650 millimeter, the radius of the crank is half of this 325 millimeter. So for the radius of the crank for C and D, it is 0.325 meter. Right. Since it is 325 millimeter, it's 0.325 meter. Right. So now we have fixed all the radiuses. Now we are going to find the centrifugal force. We know the centrifugal force is m r omega squared. So we have m here, r here. So we'll divide the m r omega squared by omega squared. So we will have only m and r. So we'll multiply this one with this one. In order to reduce the complexity, we'll reduce it divided by omega squared. Right? So if I multiply this with this, we will have for A 31.25, for B 0.675 MB, for C it's 94.25, for D it's again 94.25, for E 0.675 ME, and for F it is 31.25. Right? So this is the data for the force polygon, that is centrifugal force data. Right? Now we'll fix the distance from the plane. Right? So we have a reference plane B. Okay. So from reference plane B to A, that is 0.15 meter. Right? Since it's on the negative side, it is minus 0.15. Right? So from B to A, it is minus 0.15. Reference plane, that is 0. From B to C, from B to C, that is 0.45 meter. Similarly, from B to D, that is 0.6 plus 0.45, that is 1.05 meter. From B to E, that is 0.45 plus 0.45 plus 0.6, that is 1.5 meter. From B to point F, plane F, that is 0.45 plus 0.6 plus 0.45 plus 0.15, that is 1.65 meter. Right? So we'll fix this data of the planes here. Right? For A, that is minus 0.15, 0. From B to C, 0.45. From B to D, 1.05. From B to E, 1.5. And from B to F, 1.65. Right? According to this data. All right. So now we have fixed the distance of the plane also. Okay. So from this data and this data, we can find the couple. Couple is equal to force into distance. We have force data here, distance data here, so we can find the couple. Right? So couple equal to mr omega squared into L. Since we have divided it here by omega squared, we will divide it here also by omega squared. So omega squared will not appear in the equation. So what we will have is mrl, right? Mrl. So mr is here, L is here. We will multiply 31.25 into 0.15 minus 4.7. 0.675 MB into 0. So 0 into 0.675, that is 0. For 94.25 into 0.45, 42.4. 94.25 into 1.05, 99. 0.675 ME into 1.5, that is 1.01 ME. 31.25 into 1.65, that is 51.6, right? So this is our data for the coupled polygon, right? So now we have to see which polygon we have to draw first, whether the coupled polygon or forced polygon. So if we check with the coupled polygon, we have only one unknown value, that is ME. But in the case of forced polygon, we have two unknown values, MB and ME, right? So here we are not going to draw the forced polygon, so we'll start with the coupled polygon, right? So first we'll go for the coupled polygon, right? So in the coupled polygon, if you see, you are going to draw it according to some data, some scale, right? Minus 4.7, right? So since this is negative direction, so we have D here, right? Not D, it's A, right? So A is here this way, right? It should come down, but according to our coupled polygon, since it's in negative direction, we will draw it upside, right? Right, before that, so we'll start from D, right? So we'll come like this, D, C, F, A, okay? In this order, that would be easy. So you need to choose an easy path, okay? So for D, the value is 99, okay? So from O to D, that is 99, okay? That's in this way. You see, that's in this way. This is parallel to that 99, okay? Then we have C, D, then next one is C. So if you check with the C, the coupled polygon value is 42.4, okay? So it's upwards. So from here to there, it's 42.4 upwards for C, okay? Then we have F, right? It's this way. So the coupled polygon value for F is 51.6, right? So we will draw this way 51.6, right? Over to F, it's 51.6. So we'll draw 51.6 here, right? Then we have A, right? A is going downwards, but here our value for A is minus 4.7. So we'll draw the coupled polygon upwards, right? So that is 4.7 this way, right? If it is 4.7 downwards, that should be plus. Since it's negative, I'll draw it's upwards 4.7, right? So if you check here, we have drawn for this, and this. Since it's 0, we don't have a diagram for that. So we are left with 1.01 ME, okay? So we'll join our last point and first point with a line, right? So this line will complete the coupled polygon as well as will help you to solve the numerical. So now what we can do, we can measure this length, right? So this length will give you some value. So 1.01 ME is equal to this length. So ME will be equal to AO upon 1.01, right? Okay, right? So 1.01 ME is equal to 67.4 units. Okay, so ME will be equal to 67.4 upon 1.01. That will give you 66.7 kilogram. Right? So now we have find the ME. Right? So ME is known. If ME is known, ME into 0.675. This value is also known. Right? So if you consider the force polygon, this value is known, this is known, this is known, this is known, this is known. Only this value is unknown, right? So now we have 5 knowns and 1 unknown. Since we have only one unknown, we can draw the force polygon and find the value, right? So from this data, we now already have found the mass is 66.7 kilogram, right? So we'll replace that mass here. So we will have some value here, okay? Accordingly, we will draw the force polygon, right? So we'll start again with the force polygon, right? O to D, right? How much is the value? D, that is according to force polygon, that is 94.25, right? So D is 94.25. Then we have C, right? That is upwards 94.45. You see, that is 94.25, right? So here it is 94.25 for C. which is equal to how much? 31.25. Right? The force F is 31.25. Right? So we'll draw this way 31.25. The other one is A, that is OA. If you check with the table, A is again 31.25. Right? So we'll draw another 31.25 downwards, right, in A. Okay. And recently we have found that E, which is equal to 0.0615 ME, and which will give you 66.7. And when you replace it in the table, you will have some value. So that value is 0.675 ME. So they have mentioned it as it is. If you have the final value, then you can put it here, right? So that will give you some length here. Okay. So now we have done with all the known values. This one drawn, this one drawn, this one drawn, this one drawn, this one drawn. Now we have left with only this value, right? So according to first polygon, in order to find the balancing mass, we have to complete this polygon, right? So complete this polygon means we have to make join the final point and the starting point, right? So we join those two. Okay. So if you join those two, what you will have is this length will give you 0.675 MB, right? So that length will be give you 0.675 MB, that is equal to 45 kilogram. So if you divide it with 0.675, what you will have is MB is equal to 66.7 kilogram, right? So from here, by measuring it and fixing it on the table, you will have the balance mass B will be 66.7 kilogram, right? And also you can measure the angle, right? So if you measure the angle, this angle is given you as 45 degree, right? So you can fix your balancing masses at 45 degree here one and 45 degree there one, right? So as I mentioned earlier, since the system is symmetric, right? So they are named as X. So if you see when the answer is coming, ME is also 66.7, MB is also 66.7, right? So since that's why it is mentioned as X, because same masses are coming out of the numerical, right? You can mention it as X and Y also, doesn't matter, right? So this is the angle, and these are the balancing masses for the driving wheels, right? For the driving wheels, right? So now we have done with the driving wheel. Okay. Now we have to balance for the trailing wheel also. Trailing wheel. Why? Because it's mentioned in the numerical. We have to distribute the weights equally to the driving as well as the trailing wheels. Right? So now we'll see how to do it with the trailing wheels. Okay. So this definition is for trailing wheels. Balance masses in the trailing wheels. Okay. For each trailing wheel, the following masses are to be balanced. So we'll see what are the masses which are need to be balanced. Half the mass of the couple rod. So I mentioned already, the couple rod it's 250 kilogram, and half of it is balanced by the driving wheel, that is 125 kilogram, and rest of the 125 kilogram which will be balanced by the trailing wheel. So now we have 125 kilogram of the couple rod which need to be balanced. And the second one, we have mass of the reciprocating parts, that is 90 kilogram, which we have already found, right? So 3/4 of the reciprocating parts are to be balanced. So that 3/4 is, so 3/4 of the reciprocating parts are to be balanced. So 3/4 into 240, that will be 180, right? 180 kilogram. And in 180 kilogram, 90 kilogram will be balanced by the driving wheel. So rest of the 90 kilogram will be balanced by the trailing wheel, right? So that is this 90 kilogram, right? So mass of the reciprocating parts, that is 90 kilogram, will be balanced by this trailing wheel. In other words, the mass of the cylinder C and D to be balanced for each trailing wheel would be 90 kilogram, right? Right. So these are the masses which we are going to balance for the trailing wheels. Let's consider M-B and M-E as the balancing masses, right? Since we have used the terms MB and ME in the previous section, right? MB and ME for the driving wheels. Here we will use some other term, right? Don't use MB, ME. Except for that, you can use any other terms. So here we are using m dash b and m dash e. Okay. So similar procedure, right? Similar procedure. So first we will fix the planes. We have 6 planes, right? A, B, C, D, F, right? With similar planes won't change, right, since they are coupled, and also similar angular positions that will also not change, right? So accordingly, we will fix them in the table, okay? A, B, C, D, E, F planes, and I'll consider any one of the plane as a reference plane. I'll consider B plane as a reference plane, or else I can consider E plane also, right? Why? Because they are the unknown masses. So if we consider that plane as the reference plane, eventually we will end up the distance from the plane is 0, so which means we can have this data here as 0, which will be easy to solve it. Okay. If you take any other plane, either C, D, A, O, B, A, O, F, right? All these have known data. A, C, D, and F. All of them have known data, right? So if you take any one of these plane as the reference plane, what will happen? Any one of these values will become 0, and E and B will be having unknown values here and here. So for cos polygon also you will have 2 unknown values, and for coupled polygon also you will have 2 unknown values. So you can't start drawing any one of these, and that's why we usually select any one of the planes of the unknown mass as the reference plane. So here you can take either B or E as the reference plane. I'll take B. Alright. So the masses is going to be balanced. A, that is coupled rod, right? According to our diagram, A is the coupled rod and F is the coupled rod, right? So these two masses are 125 kilogram. Okay, so there is 125 and 125 A and F. Okay, then cylinders C and D only reciprocating parts are within the balance, and C and D, that is, we have already calculated, that is 90 kilogram, right? And C and D, that is 90. So here 90, 90. And this is the balancing mass which we need to place, which we don't know, right? M dash E and M dash B, we don't know the weight. Alright. So this is for the mass, this table, this column. And now we'll go for the radius. Right? As I already mentioned, the length or radius of the rotation of the pin of the connecting rod is not connecting rod, sorry, coupling rod is 0.25. Right? So you see the radius of the center of the coupled rod is 250 millimeter, that is 0.25. So here I have 0.25 for coupling rod A and 0.25 for coupling rod F. And the balancing masses are need to be placed at 0.675 millimeter according to the 0.675 meter according to numerical. You see here the balance masses are need to be placed at 675 millimeter. That's equal to 0.675 meter. Right? So the radius of the balancing masses are 0.675 meter. Right? And the cylinder, the radius is 0.325 millimeter. Right? So already given in the question, the stroke length is 650 millimeter, and the crank length would be half of this. So which is 0.325 meter. Okay. So now the radius is known. All the radiuses are known. Alright. So from these two columns, you can find the centrifugal force. So the formula for centrifugal force is mr omega squared. M is here, r is here, omega squared. We will usually not use omega squared. So what we will use it mr omega squared divided by omega squared. Right? Why we are doing it? In order to simply in order to make the problem simple, right? Or else we have to multiply this term with omega squared, which we don't want, right? So we will have this column into this column, that is 125 into 0.25, that is 31.25. 0.675 into m dash b, that is 0.675 m dash b. 90 into 0.325, that is 29.25. Same thing here, 90 into 0.325, 29.25. 0.675 into m dash e, that is 0.675 m dash e. 125 into 0.25, that is 31.25. Okay. So now we have data to draw the force polygon, right? But what we have two unknowns, m dash d and m dash e. We have two unknowns. so we can't draw a force polygon. So what we will do, we will now move to our next step, which is to find the coupled polygon. In order to draw the coupled polygon, we need coupled values, and for that we need the distance from each plane. Okay. So I mentioned I already considered B as the reference plane, so that is going to be 0. Okay. From B to E, right? From B to E, that is equal to 0.15 meter, right? So B to E is equal to 0.15 meter, since it's on the other side, that is negative. And then B to C, right? B to C, that is 0.45 meter, that's on the positive side, so I'll write it as it is. So that is 0.45 meter, right? So they are in meter. Then from reference plane B to D, right? B to D, B to D, that is 0.7, 0.45 plus 0.6, that is equal to 1.05, right? That is equal to 1.05. From reference plane B to E, right? B to E, B to E, that is 1.5 meter, right? 1.5 meter. So I'll write it as 1.5 meter. Then reference plane B to F, right? B to F, that is 0.45 plus 0.6 plus 0.45 plus 0.15, which is equal to 1.65, right? So now we have all the lengths between the planes, right? So now from this data we can extract the data for the coupled polygon, right? So how do we draw the couple? How do you calculate the value for coupled? Force into distance, right? So here we have the force, here we have the distance, so we can multiply this with this, will give you the couple, right? Since we have divided the force by omega squared here, we will divide the couple also by omega squared here, right? So which will give you just by multiplying this and this, right? So mr into L. So if you multiply 31.25 with 0.15, that is negative, you will have minus 4.7, 0.675 mb dash into 0, so it will give you 0, 29.25 into 0.45, that is 13.2, 29.25 into 1.5, 1.05, that is 30.7, 0.675 me into 1.5, which will give you 1.01 m dash e, okay, and 31.25 into 1.65, that is 51.6, right? So now we have the data to draw the coupled polygon, and if you check it, we have only one unknown value m dash e here, right? So we will start from the coupled polygon. Why? Because we have only one unknown, which will be easy to draw and solve, right? So we'll start with this. Okay. So we'll start with the coupled polygon first. All right. So O to D. O to D first. That is coupled polygon 30.7. Right. So we'll draw from O to D. This should be 30.7 units. Right. So I repeat again. You have to draw them according to a suitable scale, which you can select. Right. So I'll use the word unit here. 30.7 unit. O to D. Then we have C. Right. So the value of C, that is 13.2, right? So from this direction it is 13.2 upwards, okay? Then the third value, go to F, that's this direction. We'll see how much is the value. F, that is 51.6, right? So from here, this direction 51.6, all right? And then we have A, that is downwards direction, but according to our value, that is minus, so we are going to draw it upwards, that is upwards minus 4.7, right? So this way 4.7, all right? So now we have drawn for this and this. Since it's 0, we don't have, it doesn't have any values. So by joining the first and last point, we will find this length, okay? So in this polygon, by joining the starting and ending point, we will find the unknown mass 1.01 m dash e, right? So this length from A to E will give you 1.01 m dash e, okay? So 1.01 m dash is equal to 27.5 units. So by dividing 27.5 by 1.01, you will have 27.5 kilograms, right? So this m dash e is going to be 27.5 kilograms, right? So if you replace m dash e with 27.5 here, by multiplying 27.5 with 0.0675, you will have some values here, right? Some numerical value, which means this term is now known, right? So this term is known, this is known, this is known, this is known, and this is known, which means we are left with only one unknown, right? So from this, we can find the unknown value m dash b by drawing the fourth polygon, right? So we'll draw the fourth polygon, okay? So first d, right? D value is for fourth polygon, that is 29.25, right? So from O to D, that is 29.25 units, right? Then from D, that other one is, next one is a C, right? So the force value for C, that is again 29.25, same, right? So from here to here, that's again 29.25 units, all right? Then the third one, that is F, right? We are going anti-clockwise, that is F, right? So F value here, it is 31.25, right? Slightly bigger than this, right? So here you see it is F, that is 31.25, slightly bigger than this. And the fourth one we have A, or A, that is equal, that is going downwards, right? So here if you check, that is again 31.25, that is plus. So we are going to go downwards, that is also coming by this way, right? 31.5, 31.5, no, 31.25, right? So A. And now we know this value, right? We have already found this value, and the direction also we have already found. Yeah, direction we have already found, that is 40 degree, right? So from the force bubble polygon itself, you can find this angle by simply measuring it in the protractor, that is 40 degree. All right. So we will draw parallelly this one E, right, which is according to this one we have some values, right? We have some numerical value. So we'll draw it to that measurement. Okay. So which means we have drawn this one, it's done, this one done, this one done, this one done, this one done. So which means we have left with only one unknown value. All right. So we'll complete this force polygon by drawing a line which joins the starting point and the ending point. Right. So we'll join like this. All right. So from here, by measuring with the protractor, you will find this angle beta is equal to 50. Right. So the balancing mass is going to be placed at 50 degree this way. And the weight of the mass, we can see 0.675 m dash b is equal to 18.35 unit. So if you solve it, you will have 27.2 kilogram, right? So m dash b is going to be 27.2 kilogram, right? So this is for the balancing of the trailing wheel, right? This one is for the balancing of the trailing wheel, all right? So based on this data or solution that we have obtained so far, we can roughly place those weights or masses here. So if you consider driving wheel E is this one and trailing wheel E is this one. Similarly, driving wheel B is this one and trailing wheel B is this one. We have already found from this part of the numerical 67.7 kilogram, sorry, 66.7 kilogram at theta 45 and at theta 545. This is for driving wheels, right? For driving wheels, the masses are placed 67.7 kilogram masses are placed at theta is equal to 45 degree and phi is equal to 45 degree, right? So we can place them, right? So for driving wheels, 66.7 kilogram is placed at theta is equal to 45 degree. So this is the condition for driving wheels B and E. Now the condition for trailing wheels B and E, right? So what we have found, one is mass 27.5 at alpha is equal to 40, right? You see here, alpha is equal to 40, 27.5. So 27.2 kilogram. Where's it? Okay, it's here. 27.2 at alpha is equal to 40 and 27.2 at beta is equal to 50, right? So beta is equal to 50, 27.2, right? So these are the rough positions where we are going to place the balancing masses, right? So this is for driving VD, this is for trailing VD. Similarly, this is for driving wheel B and this is for trailing wheel B, right? So we have found these data. Right? Alpha we have found, mass we have found, beta we have found, mass we have found, right? So the first part of the question is over. Now we have to find the hammer blow, right? So the second part of the question, the hammer blow at 120 km per hour if the wheels are 1.8 meter diameter, right? For this, the data may be tabulated as below. So again, we are going to draw on the table. Let this one m double dash b and m double dash e. So we have used m dash e and m dash b in the previous section here, right, to find the masses. So here we will use m double dash b and m double dash e. You can use another name, x, y, o, j, k, o, whatever it is. I'm using this one, right? The balancing mass which need to be required for the reciprocating masses. Okay, so we have two cylinders C and D and two balancing masses B and D. We have not included the coupling rod here. Why? Because it is not going to take part in the hammer blow, right? So the masses which need to be balanced are 90, right? We have already found the reciprocating masses which need to be balanced are 90, and the balancing masses, they are m double dash b and m double dash e, which are going to be placed at planes B and E, right? Planes B and planes E, we are going to place the balance masses to calculate the hammer blow. All right. So these data are same. Balance masses are to be placed at 0.675 meter, and the radius of cylinder, crank, that is 0.325 meter. Same data. So centrifugal force, we are going to multiply the same 19.325, 29.25. Similar thing here, and 0.675 into m double dash b, same thing, right? And now the diameter between the planes. So I told you we will usually take any one of the plane as the reference, any one of the unknown plane or unknown mass where it is placed as the reference plane. I repeat, we'll take any one of the plane where the unknown mass is placed as the reference plane in order to make that couple zero. Okay. So I'll take B as the reference plane, that is 0. All right. So from B to we have to find C, D, and E. Okay. So B to C, B to D, and B to E we have to find. B to C, that is 0.45. B to D, that is 0.45 plus 0.6, that is 1.05. B to E, that is 1.5. So this is the distance between the planes, right? 0, 0.45, 1.5, and 1.05 and 1.5. Okay. So as usual, we can calculate the coupled value also, right? This value into distance from the plane, that is 0.675 m dash b into 0, that is 0. 29.25 into 0.45, 13.2. 29.25 into 1.05, 30.7. 0.0675 m double dash e into 1.5, that is this value 1.01 double dash e, right? So now we can draw either couple of force polygon. So in couple polygon, if you see only one unknown, then we can go for that, go with that, right? So now the couple polygon and the force polygon may be drawn, but due to symmetry, we shall only draw the couple polygon from the data given in this table, right? So based on this table, you can see there's a symmetry 90, 90, 0.325, 0.325, 29.25, 29.25, right? So there's a symmetry. So we'll draw, right? 0, we don't draw, right? Then C. So we know where C is on the upper side, right? So C is there. We'll draw C. Okay, C that is 13.2. D we already know 30.7, right? So go to D, D to C, right? And this value is the unknown value. So what we can do, we can join the starting point and the ending point, that is this, right? So either you can measure, right? Either you can measure or you can go with the Pythagorean relation also, right? According to Pythagorean relation, we know this squared plus this squared under root will give you the value of this one, right? So we have used that formula here. You can go with the usual measuring and dividing it by 1.01 also, right? Both will give you the same answer. So 1.01 MWC is equal to 30.7 whole squared plus 13.2 whole squared under root. So your final answer would be MWC is equal to 33 kilogram, right? So this MWC is going to be 33 kilogram. We know that the linear speed of the wheel, it's given 120 kilometer per hour, right? From the linear speed, from kilometer per hour, we will convert it to meter per second, right? We will convert it to meter per second. Why? Because the radius of the wheel is given in meter, right? So either we have to convert this one to kilometer or that one to meter. Okay. We can't solve the numerical while having velocity in kilometer per hour and diameter of the wheel in meter. We have to convert them to any one of the unit, right? So if you convert 120 kilometer per hour into meter per second, 120 kilometer into 1000 divided by 3600, you will have 33.33 meter per second. Okay, and the diameter of the wheel is given, d is equal to 1.8 meter. Okay, so omega, angular velocity, we know equal to v upon r, right? So r is a radius, so radius is d by 2, that is 1.8 by 2, that will give you 0.9. All right, so according to formula, omega will be equal to v we have already found 33.33 divided by 1.8 by 2, that is radius 1.8 by 2, so it should be 0.9. Okay, so omega will be 37 radian per second. Omega will be 37 radian per second. We know that the hammer blow, right? So the formula for the hammer blow is plus or minus capital B small b omega squared, where the capital B is the weight and small b is the radius, omega squared is the angular velocity. So capital B, we have already found mass is 33 kilogram, 33 into omega squared, we have already found 37, so 37 whole squared into the radius, where we have to place the mass, that's given 0.675 meter, right? 0.675 meter. All right. So which will give you, when you multiply it, 30.494 Newton. Okay. So this is your final answer for the hammer blow.